In this video, we're going to talk about what's called the divergence test. Now, the divergence test is going to be the first of many tests that we have that serves the purpose of deciding if a series converges or diverges. And as I said earlier, right, the divergence or convergence of a series is maybe half of the problem we're interested in. The true thing we're interested in is knowing what the limit is. However, in many cases, that's going to be difficult to do, and the first important half of the battle is deciding, does the series converge or does it not converge? So that's what we're going to look at and focus on in the next several topics, both in this section 10.4 and in the following sections. We're going to look at various tests for deciding if something converges or diverges. For this, we need to make a brief detour through some logic. Okay, so imagine that I make the statement, if it rained in the last hour, the sidewalk is wet. Right, so that's a statement about the sidewalk, and it's a true statement. Right, if it rained in the last hour, the sidewalk is indeed going to be wet when I go outside. So here are two questions for you. If I go outside and I see a dry sidewalk, what does it mean? Well, it means it didn't rain, right? If the sidewalk is dry, I know it did not rain. But if the sidewalk is wet, it's not clear what I know, right? It's maybe it rained, maybe a sprinkler went off, maybe something else happened. Maybe some kids had a water fight. Somebody emptied a bucket there. Any number of things can explain the sidewalk being wet other than rain. Right? So if the sidewalk is wet, I might need to then go look and get more proof that it rained. Like maybe I look at the bushes, at the grass, whatever. But if the sidewalk is dry, I don't need to look at these other things. I know that it didn't rain. Okay, so this is the importance of, or the meaning of what we say when we talk about necessary conditions versus sufficient conditions. It's if something is true, right, if it rained, then the sidewalk is wet, then rain is sufficient to explain wetness, but it is not necessary to explain wetness. Okay, so let us go and apply this in the setting of series. Right, so here we have what's called the divergence test. There are going to be two ingredients in this argument. The first one is the key fact that if we're interested in the series, right, so secretly behind what we've written, we're interested in the series sum from k equals 0 to infinity of ak, right? That's the series we're really interested in. Well, then we can look at its partial sums, right? That's a partial sum. So Sn is a partial sum of my series sum from k equals 0 to infinity of ak. But then a little bit of an algebra trick allows us to say that an is the what you get by taking the partial sum with n many terms, but then you subtract off what you get from n minus 1 terms, right? It's the difference between the n minus first sum and the nth sum. It's just going to be an itself. Now, if we suppose that this series converges and has a limit L, then we can go ahead and use our limit laws to figure out what's going on. Right, so the limit as n goes to infinity of an, we're going to use this fact right here. Right, so here we get the limit as n goes to infinity of Sn minus Sn minus 1. And now as n goes to infinity, right, we just said that this had a limit of L by our assumption over here. But also Sn minus 1 also goes to L. So that brings us L minus L, which gives us 0. So what we conclude from this, right? So what we're concluding from this is that if the series converges, right, if the series converges to some finite limit L, then the individual terms of my series have to go to 0 as n goes to infinity, right? So that's what that's telling us, and right. So here we have that if the series sum from k equals 0 to infinity of an converges, then the limit as n goes to infinity of an is 0. And, right, so from this, right, this is, I want you to think of this as the if it rained, then the sidewalk is dry form of the statement. The useful form of the statement is going to be the other way around, right? So the useful form of the statement is going to be where we take the opposite of both sides, right? So if it rained, then wet, means if dry, then no rain. We're going to do the exact same thing, right? So we're going to say if this limit of the an is not equal to 0, oops, and so if that limit is not equal to 0, then the series diverges. Right, and that's precisely the analogous version of what we were talking about with the sidewalk, right? So if the series converges, then the limit is 0. So if the limit is not 0, then the series did not converge. Okay, so let's restate that cleanly on the next slide, right? So the way it's normally stated is that if the series, right, so if that limit is something other than 0, so there are two ways that can happen, right? There are two essential ways that can happen. One of them is by the two ways this can happen are having a limit that exists but is some number other than 0, or you can have a failure to have a limit exist, right? Those are two different ways you can fail to have a limit equal to 0. Okay, so then if that happens, then we say that the series diverges. Okay, so let's give an example here. So here we have this example. It looks terrible, but we look at it and we see, oh, look, the limit of this expression as n goes to infinity, that thing converges to a third as n goes to infinity. So the series diverges. Right, so the series diverges by the divergence test. Right, so that let's write that down. Actually, let's say it diverges okay, and divergence is a long word, so I'm okay with you calling it the div test. Right, so this series diverges by the divergence test.